Dovrebbe essere.
Ok.
Sì,
Sì, ma adesso le slides.
sì, le slide, in realtà stiamo... Perfetto.
Ma il suono, sei sicuro che funzioni?
Sì, dovrebbe esserci un microfono che...
Funziona?
Sì, sì. No, quello già non va acceso, già...
Bene. Quindi prenderemo anche qui giù, guarda, in basso a destra, ecco. Non so se qualcuno può vedere.
Ci siamo?
Sì. Buon pomeriggio a tutti. Scusate per il ritardo, ma la gestione autonoma della diretta crea anche questi imprevisti. Grazie per essere qui in questa giornata, in realtà pomeriggio di studio legato alla predicibilità nel tempo meteorologico e nelle problematiche legate al clima. Non perdiamo altro tempo, i nostri relatori sono tutti qui presenti: Roberto Buizza di ECMWF Reading, Gran Bretagna, Fred Kucharski, ICTP Trieste, e Alessio Bellucci, CMCC Bologna. C'è un filo conduttore che viene declinato nelle varie presentazioni. La prima presentazione è quella di Roberto Buizza sul valore delle previsioni d'insieme, potremmo dire in italiano, per predire eventi estremi. Prego Roberto.
Ok, grazie mille Frank per avermi invitato, grazie a tutti. Abbiamo deciso di fare le presentazioni in inglese, quindi we're going to switch to English. And the plan of my talk is to go through 8 points that I think are very relevant if one wants to use ensembles to predict extreme events. Since I didn't know the background of the people who would connect, I thought it could be useful just to go briefly through the main steps that we follow when we do numerical weather prediction. So essentially, it includes 4 main processes. We accumulate a lot of observations. About 20 million observations are assimilated every 12 hours. Then we go through a process called data assimilation. Data assimilation is required to define the initial condition of the system. Observations use, and the data assimilation system uses observations at the first guess, which is a short time forecast from the previous analysis to define the initial conditions of a model. This is where we start running our forecast that runs up to 10 days, 46 days in the ensemble, 6 months in a seasonal system. What's important to understand is that clearly there are going to be uncertainties and sources of error in the way observations are collected, in the model, which is used to produce the first guess, in the data assimilation system, which is used to define the initial conditions, and then in the model that is used to run forecast up to 10, 15 days. And so this is important to understand because I'm going to discuss how we can extract valuable information from ensemble, despite the fact that there are all these sources of uncertainty. Second point I want to make is that, well, we are integrating the equation of motions of fluids, and the way we are integrating them is numerically by solving them on a grid. The grid has a mesh, which is finite. It's 10 kilometers for our high resolution system. It's 18 kilometers. It's 9 kilometers for the high resolution, 18 kilometers for the ensemble system. It covers the whole globe, and in the vertical, it has 91 layers in the ensemble and 137 layers in the high resolution system. The other last point that I want to make is what it is an ensemble prediction system. What does it mean to predict in ensemble mode? The idea is that we don't know exactly the initial condition of a system. So if this is the true state of the atmosphere, our best estimate could be a little bit far from that. Why? Because, as I said before, we collect observations only in certain areas of the globe, observations as uncertainties. The initial conditions are defined using data simulation procedures and the model. Then we run a forecast. The forecast might diverge from reality also because at one point, model uncertainties linked with way we simulate the processes, uncertainties linked to the fact that the equations are solved on this finite grid are very important. So because of the initial condition uncertainty, model uncertainties, the true state of the atmosphere might be different from a single forecast. The idea of the ensemble is that instead of running only one forecast, we run an ensemble of them, designed so that we estimate the initial uncertainty of the system, and so that we can get an estimate of a possible future scenario. And by knowing the forecast of the probability density function of future states, we can assess whether cases, extreme cases, for example, can occur. Okay. So these 4 slides should have given you a background of what it means to do numerical weather prediction. So my plan is to go through 8 points and then show 2 examples of extreme weather prediction using ensemble. The first point that I want to make is that weather predictions fail at times. Clearly, we all know about that. Even very short range forecasts can fail. And the reason why it can fail is because of what I said before. And I want to show you a couple of examples of that. The second point that I will make is that ensembles are useful provided that they are reliable. And we'll define what it means having a reliable ensemble. If the ensemble is not reliable, we cannot really extract valuable information. The third point is that an ensemble prediction system gives you probabilities. It means that to assess the quality of an ensemble prediction system, one needs to use a wide range of cases, a season, for example, and use appropriate metrics. The fourth point that I will make is that, which is also the fourth point that I'm making here. The fifth point is that, so we are talking about whether the ensembles are available to predict extreme events. Well, the problem of extreme events is that they are rare and they are quite unique in the sense that a flood that occurs in Genova in 2014 might be different than the flood of Genoa in 2011 because the synoptic forcing might be different, because the ground might be different. So it's not easy to test the current models on extreme events. The second point I want to make is that usually extreme events, when you make a prediction, populate the tails of our probability distribution function. Since we can only run a finite number of members of forecast, 50, the resolution in probability space is quite coarse. So having reliable forecast in the tails of a distribution is more tricky. We would need more ensemble forecast, 100, 1,000. Okay, so extremes are rare and are more tricky to assess how good are our systems. The sixth point that I will make is that there are phenomena which are not solved, which are not seen by our model. And so pretending or trying that they can be resolved is not correct. We need to keep in mind that our model has a certain resolution when we're trying to use them to predict extremes. But we can in some way ameliorate the situation by using appropriate calibration method, appropriate post-processing techniques that I will discuss. And the last point that I will make is that forecast skills is scale dependent. So what I'm going to do now is going to show you a couple of slides for each of these points, just to convince you of all of this. So weather prediction at time space, this is an example. The 8th of February 2015. all major weather prediction systems from ECMWF, Japan, Washington, UK, failed at day 6 over Europe, with anomaly correlation coefficients for the synoptic case dropping to 0. This is rare, but it happens. It happens a few times a year, even at the synoptic scale level. And the reason why skill drops so much is that the positioning, for example, of a cutoff law might be completely misplaced, or the intensification of the law doesn't follow what the atmosphere does. In cases like that, ensembles can be useful. How? Well, the idea is that if we look at the reliable ensemble can be useful. If we look at the divergence of ensembles, we should be able to spot situations that might be less predictable. What I'm showing here are 8, 6, and 4-day forecast skill of all the ensemble members on the cases that I've just shown you before. And what you see is that the range of skill, which is a kind of a measure of it gives you an indication of a divergence of all the ensemble members, of a spread of the ensemble, is very large precisely on the case that I showed you before when all these forecasts fail. If you look at cases before, okay, there was another one where the ensemble was suggesting the divergence is large, so the forecast, this is a difficult situation, forecast skill might be small. But usually, no, it's the spread is small, and in fact, the skill, which are the curve, the blue and red curves over there, are quite high. But then we get to these cases where, as you can see, the skill of the high resolution forecast from us, the ensemble control, the ensemble, they all drop down. And this is signaled by the spread of the system. So the ensemble can give us some information about whether the forecast can fail, provided that it is reliable ensemble. Reliable ensemble means, the ensemble gives you information. Also, if you look at the grid point, I'm moving now to the storm that hit the US in 2015. What you see here is the probability of snowfall above 30 centimeters from our ensemble. The situation was very tricky because the snow could affect New York and Boston. What you see here is a 60-hour forecast and the 36-hour forecast. What you see is that New York is on the edge of the area where the probability moved from 0% to 100%, while Boston remains both in a plus 60 and in a plus 36-hour forecast, quite within an area of very high probability. Okay, so high probability means all the ensembles were consistently suggesting Boston is going to be hit by the snowstorm, while for New York, there is a much larger uncertainty, the probability is lower. So this is the type of information that the ensemble can give you if it is reliable, and I will discuss reliability, what it means. And the way to measure or to see how the ensembles are consistent, how the divergence of the ensemble is to look at the slope of these curves, which are the cumulative distribution function for snowfall over New York and Boston. What you see is that for Boston, the curves are much more vertical than for New York at all forecast ranges, suggesting that the uncertainty is less for Boston than for New York. At the end, what happened is that New York actually didn't have a lot of snow. We were predicting 30, the US actually shut down all the transport system in New York, and they only had 20 centimeters, 10, 20 centimeters of snow, which is what's indicated here, between 5 and 10 centimeters of snow, while in Boston they had between 30, 35 centimeters of snow, which is quite close to what we were predicting. Now, all of this, so the fact that the ensemble can flag the system works provided that the ensemble is reliable. What does it mean having a reliable ensemble? As I said already, we need to assess the quality of the performance of the ensemble over many cases. So an ensemble is reliable if, when evaluated over many cases, on average, the spread of a system, the spread between all the ensemble members with respect to the ensemble mean, so the size of the ball of the ensemble is on average as large as the average error of the ensemble mean. If the ensemble is under-dispersive, it means that the spread, so how the forecast, these 50 forecasts, lie one compared to the other, are too narrow, are too tight compared to the error that one of them can have. An under-dispersive ensemble wouldn't give you information, valuable information, because it would always tend to give too high probabilities of events that might not occur. A reliable ensemble, as I tried to indicate earlier, is an ensemble that can be used to flag and identify cases which are more or less predictable. When the divergence is large, the error of the ensemble mean or over any of these members compared to the reality can be very large. So a large ensemble tells you, well, a very large, spread can tell you that the ensemble might fail. While if the ensemble is tight, all the forecasts are close to each other, it means that also, on average, your ensemble mean should be close to the reality. So you should expect error to be small. And this is what I showed you, for example, earlier in my time evolution of spread and error. Third point, why the ensembles are useful is that successive ensemble forecasts are more consistent than successive single forecasts. So this comes from a study that we did about 10 years ago. The question, one of the tricky situations that you as a forecaster, every 6 hours or every 12 hours, you are given access to a fresher, younger forecast. And forecasters tend to compare this younger forecast to the previous one. And if these two forecasts are very different one to each other, forecasters would lose confidence in the forecast. Which one should they trust? Should they trust the younger, because it's the most recent, or the oldest? So what if the oldest 1, 2, or 3 forecast all suggested a certain event, and now it changes? Should they trust the oldest because I had 3 consecutive forecasts telling me that the situation was going to be cold weather, or should they trust the younger one because it suggests actually the weather is going to be average, or the temperature is going to be warmer? So, and why do forecasts change so much? Because now we start from new initial conditions, there are uncertainties growing, and this is something that we don't really like. If instead of using a single forecast, you use the ensemble distribution, if the ensemble is reliable, you should expect that this jumpiness between one forecast and the successive, valid for always for the same time, should be less. And indeed, in this work, we showed that to take, for example, the ensemble mean, the average distance between an ensemble mean, say, forecast at day 7 and the one 12 hours earlier, is much less than the difference between the 2 control forecasts, 2 single forecasts. And the longer the lead time, the closer, the more consistent the ensemble mean forecasts are compared to the to 2 control forecasts. This is valid both from the ECMWF ensemble and the UK methods. Let me just state, without going into details, that to build this curve, you need to take into account the fact that the ensemble mean, because it's an average forecast, it has less case, less variability. So the curves have been generated by taking this into account and renormalizing the difference between 2 forecasts, taking into account their variability. And in fact, we have defined in this paper what is called an inconsistency index say that. What you see is that clearly as we go closer, so in the shorter range, there is much less difference between single and ensemble forecast. So the ensemble provides, or at least the current ensemble provides, more valuable information as the forecast lead time increases. Fourth point is that ensembles must be evaluated using appropriate metrics. This is important because at times I read, for example, on the newspaper, oh, the ensemble prediction system failed, and they were referring, or I hear colleagues even saying the ensemble failed at least in predicting this event. Well, it's interesting, and one must look at how an ensemble performs at single events, but to be able to assess the performance of an ensemble, because it gives you probabilities, you need to evaluate them over many cases. So I explained to you what is an ensemble. It's used to build this probability distribution function, and one needs to look at very many cases to be able to assess how good they are. And the way we do that is to compute for all grid points over an area, for many cases, usually season, the distance between an ensemble forecast distribution, blue line, and an observation, and compare it with the distance between a climatological distribution and an observation. The ensemble, if at short lead time, there is clearly the ensemble is beating a climatological distribution function. As the forecast lead time increases, there is at one point a time when the ensemble doesn't give you any extra information compared to climatology. So we define that as the forecast kill horizon up to which the forecast is valuable. But what is key is to do this considering very many cases. And one of the measures that we use is the continuous run probability score. And another measure which we use is, for example, ROC, the relative operating characteristic curve, and the area under this curve. Now, this is another important point that I want to make. An ensemble gives us probabilistic informations. If I predict with 80%, if my forecast gives me a probability of 80% that an event will occur, I would expect, if the ensemble is reliable, that 80% of the times that event will occur. But I cannot expect that that event occurs 100% of the time. Okay, so the ensemble gives you more information than a single forecast, but it never gives you the certainty that something will happen. Okay, this is an example of a ROC curve, which is based by looking at the heat rate and the false alarm rate of ensemble probabilities with intervals every 10%. For example, in this case, we're looking at monthly forecast or weekly average and 2-meter temperature anomalies in the upper tercile, so warm anomalies over Europe. It's one season. The area under this curve is giving me an information on the scale. It's 0.87. But if I look at the specific case, for example, when my probability forecast of 2-meter temperature anomaly in the upper tercile, so warm, is 60%, this is what I see from this curve, that I have a heat rate of 80% and the false alarm rate of 20%. So 20% of the times, if I use this probability to take actions, I will fail. The forecast will be wrong. But 80% of the times will be accurate. Okay? Clearly, there are forecast variables which are easier to predict than others. This is the same type of plot, but for total precipitation. This is also a day 5 to 11 forecast, same area. It's a probability of precipitation in the upper tercile. As you can see, the curve is closer to the diagonal, which is the line of no skill. The area is 0.73 and not 0.85. If I take the same probabilistic forecast, 60%, then my heat rate now goes down to only 56% of the time. Now let's move further ahead into the forecast. Then with precipitation, we go to try to predict the same type of anomaly at week 2, between day 12 and 18. Now the curve is marginally above the line of no skill. We still have some skills in the sense that the heat rates are still higher than the false alarm rates, but it has gone down a lot. So as we go into the forecast, predicting events become more and more tricky, and this is signaled, for example, by this type of statistics. Extreme events are rare. I mean, as I said, because I'm going to show you a couple of examples. Now, I said that the probability distribution, so that extreme events populated the tails of a probability distribution function. Given that we're running only 50 members, the resolution probability space is coarse, which means that the uncertainty in predicting the extremes is larger than predicting normal events. As I said, the evaluation is difficult because there are only very few cases, extreme cases in the past, where we can test our current systems. But despite that, we are trying at ECMWF when we upgrade the system, the model, to assess how it performs also in extremes. So the way we do it is by following a twofold process. First, we test on as many as possible extreme events of the past, maybe 10, 20 cases. And then we look at events which are maybe a bit less extreme, but at least where we can build a more sound statistics. In this way, we have an idea of how the system performs on a bit less extreme events, and we have the sound verification, and then at least we have some indication on the extremes on how it's performing. Resolved and unresolved scales. Again, I read often that when there are extreme events like flood in Genova or flood of Livorno, the forecast failed. Well, the forecast failed. The forecast or you read that despite all the investment in developing models or in supercomputing, we're still not able to predict certain events. Well, it's not surprising if you think that we are resolving the equation of motion on a grid which has a certain spacing. So the model doesn't see processes below that scale, but actually it's even worse than that. If you take this plot compares the energy spectrum of observations of wind against the energy spectrum of our models. What you see is that even a model with a 10-kilometer resolution actually has a spectrum of kinetic energy which matches the observation only up to about 4 to 6 grid spacing. Okay, so the very fine scales are not simulated accurately enough. Why is that? Well, because to make it possible to integrate numerically the equations with a time step which is not too short, so that we can finish our integration in a reasonable time, we have to apply certain processes, dissipation processes, and this means that the finer scales that the model simulates are not actually simulated as well as in reality. So even if our grid point is 9 kilometers in the ECMWF high resolution, the scales which are simulated well, where the model has the same statistics as observation, are actually about 50 kilometers. So ECMWF highest resolution model has a natural resolution of 50 kilometers, the ensemble of about 100 kilometers. Okay? If you're running a model with 2 kilometer resolution, you're not resolving actually the scales up to 2 kilometers, but most likely I would say 2 times 5. The role of statistical proportion. So because of what I said, clearly we cannot expect also the model to capture the extremes that we see in reality. The orographic forcing, the intensification of convection development, the wind gusts that we see in reality are not captured in a model. Okay, and this is an example again on a paper that we did 7 years ago, where we looked at statistics of wind extremes and temperature extremes in the ensemble and at the observation. We have been trying to apply extreme value theory to try to extract more information from the ensemble. So what you see here is an example of a result discussed in the paper. It's temperature, maximum temperature. We're looking at the prediction of heat wave. So this is maximum temperature for a grid point, Hanover. Here are observations. So we had about 100 observations. We're showing only a few of them. And what you see in solid is an extreme value fitted curve and the range of uncertainty. So if we look at the 10-year returning period of the observed maximum temperature in Hanover was about 36 degrees. Then we took exactly the same 20-year period for which we had a lot more ensemble forecasts, because we had reforecasts which are, we had about 10 times more. So again, we fitted our extreme value curve, we have a mean, the uncertainty is less than for the observation because we have more points. And then you look at the 10-year return period in the model climate, and you see that it's only 34 degrees. So this means that when a model gives you a probability of 34 degrees, means I'm giving you a prediction that an event with a 10-year returning period can occur. In reality, I should expect actually 36, higher values. And the same can be applied to precipitation or wind gusts and so on. So because of the model approximation, because of the scales that the model resolves, there is a difference between the extremes that the model can see and the extremes that we see in observation. But if we take this into account, if you apply, for example, sophisticated post-processing techniques like what you could do with extreme value theory, we can try to relate a model anomaly to a real forecast anomaly. And there is a way that we used to do it, which is to compare a model climatology with a forecast, the model climatological distribution function of an event against the forecast distribution function, the latest forecast, and the area between these two curves, if it's very large, it indicates that we are expecting a very extreme events. Extreme events that would translate in real world into values which are higher than what the model sees. But at least we can use this type of product, which is a renormalized product, if you want, a post-process product, to tell us something about what could occur in practice. The last point that I want to make is that forecast skill is scale dependent. There are certain scales, the larger scales, the slowly evolving scales, which can be predicted for longer period than the fast small scales. And the following talks will actually discuss some of these points. I just want to make the point that this is again from one of the most recent results, where we try to estimate what is the forecast skill limit for different time scales. And what you see is that the very small scales have a predictability limit is only, say, few days, maybe 10 days. High precipitation values only a few days. But if you're trying to predict synoptic scales or average anomalies over large scales, then the predictive, the forecast skill limit is maybe a season, few months or 1 month or a season, or for some events like El Niño SST anomalies, you can go up to a year. So this is, we think, a nice way to keep this in mind. It's not as we were used to think following works in the 60s and 70s of Lawrence, that butterfly effect, there is a forecast skill limit of 15 days for all scales. following that work, other people, Shukla, Hoskins, and others, showed that actually there is still, for one larger case, we go beyond this 2 weeks time. Okay, now let's try to apply all of this thinking to a couple of cases, to a couple of extreme events. So this is one of our forecasts for a case that we'll reveal afterwards. It's the map of the extreme forecast index. Extreme forecast index is that index that I described earlier, which measures how far is the distribution of the current forecast from its climatology for total precipitation. This is a forecast day 7 over Europe. Yellow and red are the areas where we're expecting an extreme event. You also see some contouring. The contouring tells us something about the extremes, the tails of the distribution. Areas inside these red contours are areas where not only we are expecting an extreme event, but the event can be really extreme. So, by looking at this, now you see that there are some areas pointed out by the ensemble where there might be extreme events. If we didn't have an ensemble, we couldn't build such a map. The only way to predict such a map is that you have a good estimate of the model climatology that gives you the probability distribution function of event and a good estimate of a forecast PDF. With one single forecast only, you could only show one forecast. That day 7 might, as we all know, not be correct. Now we move to day 5, and what you will see is that some of the contouring have become stronger. So the EFI, extreme forecast index, has moved to higher values, particularly northeastern Italy and the western coast of Italy. So all these are areas where some extreme event might occur. Then we get to shorter lead time. I showed you earlier, for example, that the ensemble give us more valuable and less jumpy information from day 2, 3 on. So now we're getting to the day 2 forecast range. We look at the high resolution forecast from ECMWF. And now we start seeing quite high values, 100, 150 to 115 millimeters of rain in some regions. Now, when we see such a single forecast, if we keep in mind what we have seen the days before, day 5, so one day before this, and day 7, so 3 days before, that there were regions, for example, in Italy, where something extreme could happen. Now, as a forecaster, you know that something might happen. High resolution forecast confirms that something like that can happen. And then we get to one day before the event, an extreme forecast index is extremely red, 1. So an extreme is happening, there are contours of the shift of tail suggesting it's also an extreme. So the tail of the distribution is far from the tail of climatological distribution. The area is still large. There is still a lot of uncertainty of where is an extreme event going to happen. Even at day 1, we don't know for sure where, but we know that if we are an Italian forecaster, we might expect an extreme event along the western coast from, say, from Tuscany down to the end of Campania, maybe in the northeastern part of Italy. This was the case of a flood of Livorno, 152 millimeters of rain. There was high precipitation also at another part. This is a map of the observed precipitation. But now, as you can see, the ensemble in some way told us that something was going to happen. But as I said before, the ensemble is only because it has a 18 kilometer resolution results case only up to 100. There is a lot of uncertainty and so on. So it doesn't only tell me it's going to we're going to see an extreme event in Livorno. But it is flagging the situation as a situation where extreme events can happen, and it is having a signal also where it occurred. The second case, this is again a 5-day EF5 of the precipitation. It's a large area of high values. Again, if you are an Italian forecaster, you would be interested in keeping an eye on what was going to happen in Liguria and in Piemonte. Then I'm going to zoom in into a particular place, which I'll tell you later what it is. And if I look at the forecast from 3 days onward, EFI above 70%, getting to red, getting to 80% at day 1, red, which means shift of tail, so possibility of extreme events in the very short range. This is the full distribution of precipitation predicted for that particular location that I'm going to discuss in a minute, 5 days before the event and 2 days before the event. So it's clear that something is coming. The ensemble is signaling large uncertainty of a amount, but no, it's 25 millimeters every 6 hours for 2 days. It means a lot. It's 115 millimeters for a model that rarely predicts above 100 millimeters of rain. This was the case of Genoa, 5th of November 2014. This was the forecast 8 days before the event for Genoa. Some indication that the regime is changing, heavy precipitation is coming. A lot of uncertainty, but the signal is there 5 days before, is there 1.5 days before. Now, predicting exactly where the flood is going to occur, east of Genoa, west of Genoa, no, it's impossible. The model doesn't resolve this case. But the area in a grid box around Genoa, resolved by the model, so 50 kilometers plus or minus that area, there are clear indications from the ensemble, even if there is uncertainty, that something extreme could happen. So, concluding, I tried to give you an overview on how I think ensembles could be used and should be used to predict extreme events. They can help us if they're reliable. So not all ensembles can help us. They must be reliable if we want to extract valuable information. They must be evaluated properly. We cannot judge an ensemble prediction system by looking at one event only. We need to collect statistics on very many. Extreme events are rare, so are challenging also for ensemble system. But if you apply clever post-processing techniques, so which you can think of them as kind of renormalization, we can extract information from these ensembles, even if they're coarse and they don't resolve all the scales. Forecast skill is scale dependent. And with this, I conclude my presentation. So I hope that I've convinced you that they should be used, they can be used, they can give valuable information. Definitely more than single forecast, even for the short range. Thank you.
Thank you, Roberto. Grazie, Roberto. Questions? Domande? Curiosità? Dubbi?
Just one thing, Roberto. Probably for weather forecast, it's not the case, but you are aware certainly of this fact that at the Met Office they're discussing for the seasonal forecasting range this signal-to-noise paradox, where the ensemble suggests there's very little predictability, but comparing with observations, they sometimes find, or there seems to be quite high predictability. How would you comment on those kind of situations?
I think We have done similar studies in the past for the ensembles in looking at grid point values of synoptic scale weather events, by looking at how the ensemble would perform in an ideal scenario where we pick one ensemble member's verification, and in reality. And actually, they are not very dissimilar, which means, and in fact, if we think about the reliability of the ensemble, the medium range ensemble are not too bad. We are still, for some variable, underestimating the error. So the spread is maybe 10, 15%, 20% too low. But the underestimation is not very large. There is no overestimation, which means that because the ensemble is quite well calibrated, I think it's less of an issue for the medium range than if you go longer range. In longer range, I know about what to say. And the points that I made about the tails of the distribution and the ensemble size, resolution probability space, I think it's very relevant for the longer range. From studies that we've done at this scenario, it looks as if you go to the sub-season and season time range, you might need a lot more ensemble members to be able to have a better reliability and a better signal to noise ratio. So 50 members is not enough. Maybe we need 200, 300.
Other questions?
Yes.
Paolo?
Maybe slightly off topic, but what's the strategy of ECMWF to improve the reliability? So what do you have to do for the reliability?
So the ensemble is not reliable if we are not able to simulate properly either the initial uncertainties or the model uncertainties. We believe that with the initial uncertainties, we are not too bad. We keep improving our two methods, single vector and ensemble data simulation. So in June, we're going to 50-member EDA with a revised stochastic scheme so that we know that the spread of EDA is improving a lot in the PBR. So this is going to give us a more reliable system. But a lot of focus is now on the model uncertainty. We think that the model uncertainty schemes that we're using can be improved a lot more. And we believe that if we do that, we will improve the reliability of the system. So we're thinking about the processes, the sources of error, and we're trying to improve them. And as a result, we expect the reliability of ensemble to improve. Model uncertainty scheme is going to be revised in June substantially when we implement the new model cycle, and there is a lot more work in trying to really change the schemes in a couple of years.
Other questions?
Well, I just have a curiosity, an innocent question about the slide where you had drawn the rain gauge distribution over Italy for the case study in Liguria. So why do you have such a few rain gauges in Italy?
Okay, because at the European Center, we only receive routinely data from CNOP stations, full stop. We receive data from high-density networks later on. Maybe once every month or two, we get a bunch of data sent to us. So these are plots that I took from the work with this when we were predicting, and this the day after. So at few days after the event, we can only build this type of plots. These are built routinely. So routinely, we show what we receive, and this is what we had. Probably if you now go and look again at this case, in our database, we can get many more observations, but they're not used in our model. So all the observations you see here are used, precipitation not initialized, but if I show you a map of CNOP, all the CNOP data we receive go into the data transmission system. Okay, so this is why you don't see much here. You see maybe, no, but
There is a difference.
Yeah, there's a difference, but it's but this is the main reason. Yeah. And then some countries send us data every day. Others, like Italy, I know that we get now identity network data, but every 2 or 3 months we get a few months. Yeah. So this is why it's very poor. While maybe here we are already receiving data because maybe they are sent as they are collected.
I have a question. What about the nesting of mesoscale ensemble models into the global scale ECMWF model? Is there any specific receipt? Because you can handle and improve the scale of the predictability. Is it model dependent?
No, I think, okay, I think, for example, France has been developing a lot, not just the limited area ensemble, so the model, but also the limited area data simulation system. So I think clearly you can extract more information if you nest a high resolution limited area model because you might resolve better the forcing, the Lenzi mask, the orography, the different characteristics of the soil. But, for example, the different characteristics of the soils, if you initialize the soil using extra data that you might have, then you can gain a lot more. So in France, we have done a lot to develop high-resolution data simulation system so that they can initialize also the finer scale using minimal data than what we use.
So adding more information at a higher scale. So that's
So it's not just having a high resolution in the forecast. Ideally, you want to initialize also the smaller scale. And to do that, it's not enough to nest. You should nest and have your own limited area initial conditions. And then you can use our ensemble to guide as a boundary condition, but you want to have initial condition done at high resolution to extract even more information. But it's a strategy that I think it's the right one. That we run up to where we can. Now it's 9 kilometer high res, 18 kilometer ensemble. In 5 years it will be 9 kilometer ensemble, and the limited area model go down to by a factor of 5 to 10. And as we increase resolution, we should, in this way, there are scales that we will never be able to see, but the limited area model will be able to see, and in this way we will be able to give better prediction of the extremes.
Is there any scenario where there is a surpassing?
No.
Or this political decided?
I don't think so.
Down to.
No, I think there is. No, I don't think so. I think we can work and complement each other. But probably there is a point where the gain in having a nested limited area model, if you don't initialize the small scales, is lost. Actually, it can damage it if your model is not well tuned. So this is because now when we initialize our model, we're using our model. Our initial conditions are consistent with our model. If you use our initial conditions in a model which has a different surface schemes or different type of parameterization, you might introduce imbalances in the short range that are going to hit you exactly in the short range where you want to improve. So there will, at one point, you will gain by having a nested limited model only if you also have a high resolution in a data simulation procedure to initialize the small scales.
Otherwise,
with your model, yes.
Otherwise, you are damaging.
Yes.
Okay.
Thank you.
Thank you again.
Yeah.
So it seems the live streaming is working. At least this is our agents at Lavana are telling us. I think this is time of Fred Kucharski from ICTP in Trieste. And Fred is going to talk about teleconnections, about Europe and El Niño southern oscillations in different seasonal conditions. Please, Fred.
Yes, thank you very much, Chetans, for letting me talk and being here to listen to me. I'm moving right down the scale that Roberto showed to the long time ranges and to the large spatial ranges. So we are talking now El Niño, teleconnections, which means we are talking about seasonal forecast essentially, when we are talking about forecast, essentially seasonal outlooks. And I also don't promise to answer many questions here. Probably there will be more open questions after the talk than before. And so you see my co-author list is also Paolo, who contributed a lot actually to this kind of assessment. So this is a summary of essentially 3 studies plus some other things. A recent paper by Martin, published in BUMPS, which he came across this strange case that teleconnections change actually. So probably, at least myself, I was reminded that there is El Niño that is important in 2015, 2016, when suddenly all over the news, not all over the news, but in some news, there was the mentioning of this large El Niño event coming up. And it turned actually out to be probably the largest event in the last at least 50, maybe 100 years. So very comparable to the very strong 1998 event. And we had strong anomalies also in Europe, but of course there we know that it's one El Niño event, we observe an anomaly, the attribution problem is a very difficult one. But we got kind of reminded that, okay, El Niño is there, what do we expect in Europe, for example? In the United States, people know exactly what are the expected influences of El Niño. So in other tropical regions, people typically know there are typical ENSO teleconnections. But in Europe, we don't know, actually. And the reason is perhaps that there is none. Because if you look at this map, you see for different seasons, up there is winter for El Niño, winter for La Niña, and then summer season for northern, for the warm phase and for the cold phase. And you see the teleconnections that can be warm events, dry and wet, all over the globe, distributed somehow. But if you look at Europe, you see it's blank. So we can, in principle, forget about it. However, one should be a little bit more generous with this. No, in these kind of maps, you would only draw probably those teleconnections that are really robust in the sense that you expect from every single El Niño or La Niña event a signal when it happens. You may find, looking at a long statistics, actually some kind of signal, some small change in the probability distribution, even in other places than here. For example, I can just mention that in summer, you get a drying in the cell, you get a kind of a rainfall dipole also here, which is not shown here. So anyway, it could make sense to look further into Europe. And actually, Martin, when he looked into this, came across this. So what about maybe, you know, often people look at the traditional seasons, which is winter, December to January, February, or March, extended, or summer, maybe just June, July, August. But what if we consider other seasons? Maybe there is something. Just dig a little bit around. And there's actually something interesting going on. So this shows for the reanalysis data, so as close as we can get to observations, the ENSO composite for this is a projection here where we look on the North Pole now. And these are 2 levels here. The upper one is the 500 hectopascal height, and here is the 200 hectopascal height. And shown is the height at that level. So this can be interpreted, as you certainly know, as the kind of at the pressure at approximately maybe 5 kilometer height or at 10 kilometer height. So essentially, the air is flowing along these lines of constant geopotential height. And as you can see, it's quite interesting how actually in November, particularly at 500 hectopascal, we see quite a strong signal. This is for everybody who works in the field. So this is almost 50 meters there in the reanalysis. It's quite a strong signal, statistically significant. And it's even more interesting to see that in the Pacific, there's a relatively weak signal in November. Whereas if you go on later in the season, you see, if you consider the European region, it seems that the signal almost switches sign. It goes from, where it was blue before, it's red now, and opposite. So it's almost the opposite sign. And it becomes much stronger in the Pacific. This is kind of more the classical picture that you expect from an El Niño teleconnection, is what happens in February. Whereas this is a little strange. I mean, El Niño is happening in the Pacific, so why do you get a strong result in the European region? And so we dig deeper into it and look at the consequences for Europe. And the consequences for Europe are actually quite stunning, because in November, we find a very statistically significant warm anomaly covering the whole European continent, and also Italy, the whole Central European continent, essentially. If you think these are composites, they are kind of taken, so they are referring to typical, like one standard deviation of sea surface temperature variations in the Pacific, which is less than 1 degree. If we have an El Niño event, that would amount to 2 to 3 degrees. In the last event, more than 3 degrees. So we'd expect in Europe probably something like more than a 2 Kelvin or 2 degree temperature perturbation, which is quite substantial on a monthly timescale. So, and this is actually, if you go, for example, to other seasons, you hardly see any statistically significant response in Europe. So there's something very interesting going on in November. And also there's not as quite as significant, but also indication of quite wet conditions, particularly in Western Europe. And then dry conditions if you move to the east. So quite interesting response. So there's something, this would indicate some predictability, because now if we have a seasonal prediction in October, we can, El Niño, we hopefully can predict a warm November in Europe or something like this. So something more than maybe before was guessed. So the questions now would be, so in autumn, we have this kind of what people call positive North Atlantic Oscillation type response. You've all heard about the North Atlantic Oscillation. Some people say, oh, this is actually not the North Atlantic Oscillation. There's a little bit of a debate, because everything that looks a little bit like the North Atlantic Oscillation, people call North Atlantic Oscillation. Others would call it as a different pattern. It doesn't matter. The important thing is that this kind of switches sign to the opposite, which I call negative North Atlantic Oscillation type pattern. But people may call this, in fact, Martin in the paper has called this Atlantic Ridge pattern, which is another famous pattern that happens in the North Atlantic. But it doesn't really matter. Important is that, for example, the impact on the surface air temperatures in Europe is very significant. So we get a very strong signal there. And the strange thing is that there's no clear wave train from the Pacific, which is, I will show this later. We expect that there should be a wave train from the Pacific if we want to have an impact in Europe. So the question would be, what's going on? Is this systematic? So we have analyzed this further by looking at the westerly wind. Well, this is zonal wind in the Atlantic region in the mid-latitudes. So this is kind of indicating how much warm air is evacted from the Atlantic into Europe, this index. And this is showing time evolution. And this is showing the vertical surface and then going up to 10 hectopascal. And it's quite interesting to notice that in November, we get these positive anomalies, which means westerly wind. It's consistent with warm anomalies in Europe. And this turns, when we go on to late winter, into easterly, more likely easterly winds, also statistical significance, and an interesting connection with the stratosphere. Whereas the response in November is completely only happening in the troposphere. So very interesting, and it seems quite systematic changes, because these are statistically, where these crosses are, this is at least statistically significant. If it's relevant, it's another issue. Maybe this is not relevant because we didn't see much of a surface temperature signal in Europe, but this is definitely relevant also. So first, I want to discuss the late winter response, which has been much more analyzed. And so there are many studies, actually, even though on average there's very weak response, but people have still analyzed it because we want to be sure. And also this apparent stratospheric connection that we could see in this diagram has been analyzed. So what's the basic idea? The basic idea is when we have El Niño happening in the Pacific, there's an enhancement of precipitation, and we get upper level divergence, and this acts as a source for Rossby waves. So we get an input in our vorticity equation, and then the waves propagate away. And that happens, the theory tells us, that happens in great circles, ideally, in the most simple case, from the Pacific towards North America in this way. So this is the reason why we expect this kind of wave train that theory tells us should be there. This is the reason why we expect the signal first coming from the Pacific and then entering maybe into Europe or modifying the climate in Europe. But then obviously that wasn't the case. And this, for example, again for the flow at upper levels, we can clearly see, this is probably even already a model result, that this is very clear, this wave train. And then somehow it enters Europe. This is for winter mean, okay. So what people have then discussed is, okay, there seems to be this clear what people call stratospheric, tropospheric pathway, which goes in the lower levels of the troposphere. But there's also something that people call the stratospheric pathway, that these waves that are generated, they are throughout the troposphere and enter also the lower stratosphere and modify the circulation in the lower stratosphere. So both pathways have been discussed. And we have tried to, with a very simple low-resolution model that I like to use, and also Paolo likes to use, still likes to use, we've analyzed what's going on again, even though this is already kind of a well-established theory, what's going on, but doing very idealized experiments. So we prescribe kind of an anomaly in the Eastern Pacific. We prescribe climatological SSTs elsewhere, do 2 experiments, one with this anomaly, the other without this anomaly, and see what's happening, essentially. Try to analyze what's going on. And we start in January with our simulations, and the model in the upper level flow predicts this wave train, which is kind of classical. But then it seems, if you look at it, if you look to February, it seems the flow seems to be more zonally symmetric almost, and particularly in the polar regions, there's this indication of getting all high values of geopotential height in the polar regions. And this is even more clear if we look at surface pressure. So surface pressure in January still has this wave train. Then February, we tend to get already this high pressure to the north. And then already March, if you look at the model simulation, has clearly this dipole in pressure, surface pressure, which would, in this case, weaken the flow in Europe and tend to cool off the European continent. So the flow would be around this here. So that's the clear tendency also in this simple, very simple speedy model to get kind of a negative North Atlantic oscillation type response if we go later into winter. So what's going on in the model? Oh, and this is if we look at the same picture, look what's happening in time. And in the vertical up is the temperature at the polar cap. So essentially the whole polar cap, the whole column is warming up due to the heat fluxes, particularly the stratospheric levels in the model, which are only 2. And this is clearly having a structure, quasi-barotropic structure that extends through all the levels and reduces the westerly flow in Europe. So we try to assess this further. This is an analysis that also Paolo did in his PhD thesis. In fact, we have kind of copied that technique, but it's been introduced by Hinson and Ambaum, who argued that it should be the meridional heat fluxes, so the waves that are generated by ENSO, they modify the wave, the eddies in the upper troposphere, lower stratosphere, and they modify the heat fluxes into the polar region, particularly here in the upper troposphere, lower stratosphere. So we calculate these heat fluxes in the model, and it's a very clear picture. So we start from 0, and then there are positive heat fluxes into the polar cap in the upper and the lower stratosphere, essentially. And then as we turn off this El Niño event in the model, they decay. So the model produces these kind of heat fluxes into the polar stratospheric, lower stratospheric cap. This is just another picture of the same thing. Then we wanted to ask the question, okay, we can show that the polar cap is heating up, and some theories tells us that this signal may propagate downwards. The mechanisms are not so well understood, but at least we wanted to check in the model if we simply warm, we put a heating in the stratosphere, in the polar stratosphere. Is this signal really propagating down in our model? We just tweaked in the equation and put this heating there, just for 1 month. So that's just heating up. But interestingly, in the lower levels, it gets cooler. And in fact, in terms of geopotential, there's this downward propagation. So kind of, even the simple model, it seems to work. And it seems quite instantaneous, actually, in this model. So as soon as the signal reaches the tropopause, it's essentially, within a few days, it's propagated down. So since it works in a very simple model like SPEEDY, it has just very few layers, also Paolo, I think, convinced me that it should be a very simple mechanism that is working in this model. And the only mechanism that I understand more or less how the troposphere-stratosphere interaction works is the following. So some of you probably know that this general conservation law for potential vorticity, which in a simplified version for a barotropic fluid takes this simple form, where up there is the relative vorticity, so the absolute vorticity plus planetary vorticity divided by the height, in this case, of the tropopause. This law can become more complicated if you have a compressible medium, but to make the investigation simpler, we have simply assumed, okay, let's the h be the height of the tropopause. Then if you warm the lower stratosphere, what would happen is you bring down the tropopause. If you bring down the tropopause, you change the height. If you do that, you have to change the vorticity. If you reduce the height, you have to reduce the vorticity. So the westerly flow that we have originally may weaken later. So this would be the very simple mechanism that I would propose, how it must work in SPEEDY, because there's not much more going on in this very simple model. So this is how SPEEDY could kind of predict this late winter warming of the polar cap and the negative Arctic oscillation response. But we found in a later study that also there may be an even further delay going on that may influence European climate even up to late spring, early summer. And so in order to investigate that, we also put a SLAP ocean, so an ocean model that can react to heat fluxes from the atmosphere, not moving ocean. We thought on a seasonal time scale, it may be enough to have just a thermodynamic ocean model. And we wanted to address the chain. So if there's a wave train from the tropical Pacific to the mid-latitudes that reaches the North Atlantic and then can interact with the surface, maybe it may induce sea surface temperature anomalies in that SLAP region
that can persist and influence climate in the following summer even. So this is actually from this simulation, the temperatures that remain from winter in April to June. So already this 3-month shift. They simply persist there. And it turns out to be this temperature gradient between the tropical region and this more exotropical region, purely induced by heat fluxes from the pressure patterns in the North Atlantic. And we compared the simulation of having this mixed layer with not having it. And it seems that if we look into April, they are still really similar. But later in spring, the mixed layer simulation in the North Atlantic shows much more persistence. So this kind of this is a low pressure system, extends further into Europe, and we get this persistence of this negative Arctic oscillation type picture. And in fact, if we look now at observations, there was this strange signal that if you take the first, it's a principal component, so the largest variability pattern in Europe in late spring is this dipole between wettening in Central Europe, even extending into Southern Europe, and drying in the northern region. And if you relate that to what's happening in the Pacific, but not instantaneous, but with 3 months before, so the winter El Nino, you see this correlation. So in order to solve this puzzle, we had to argue that okay, the Pacific El Nino anomaly modifies pressure patterns in Europe, in the North Atlantic region, that then can delay this signal by 3 months. In fact, the model shows very similar results. So we get this dipole, coarse resolution model, so we don't expect it to be exactly similar, but we get this dipole of rainfall that is related 3 months before in our SLAP simulation with El Nino type anomalies. So this can be explained. We are happy with it, so that's all fine. So we now have explained how the Pacific modifies the waves in the El Nino event, modifies the waves in the northern hemisphere, may modify the stratospheric vortex slowly by this meridional heat fluxes. And at the surface, the pressure pattern influences the surface temperature in the North Atlantic that may then even delay the signal into late spring, early summer. But what about the autumn? What about the autumn problem? We haven't addressed that yet. So for autumn, at least there's one hint, because the good news is that if we compare the observed signal, November, December, February, with the ECMWF system 4, this is the seasonal forecasting system, the previous version of the seasonal forecasting system of the ECMWF model. Like we haven't yet had the latest forecasting system, but there is this tendency that the model has this positive NAO-like signature in November, and then it turns clearly into a negative North Atlantic oscillation-like signature if we go later into the season. Maybe if there are biases in the middle, one bias is that the wave train from the Pacific is perhaps too strong in November already, whereas in the observations it looks very weak. But this seems to be a bias of many models, actually. So what could be the reason? In fact, I don't have an answer, but one idea would be that it's actually a tropical kiloconnection. So we discussed one, this is kind of a picture composite of upper level divergence expressed here by the velocity potential. So one of these divergence centers, upper level divergence centers, is in the Eastern Pacific. So the air goes up, causes upper level divergence, but it typically comes down somewhere. It turns out that in autumn, that's the case in the African Indian Ocean region. So another source for Rossby waves, and we see this here in the stream function, could be actually located in the Atlantic region, for example. It's one hypothesis that also Martin has a little bit investigated. So you can actually plot this Rossby wave source, which is essentially vorticity times divergence plus some other terms, but it's mainly the source of Rossby waves that may be generated by upper level convergence. And indeed, it seems there is something interesting going on in the Caribbean, but the picture is extremely noisy. So we were not very much convinced that this is actually the final solution. And so this is still an open question. If someone has ideas how to solve this puzzle, it's welcome. I know that some people from the UK Met Office, they're analyzing this also. They may be very close to a solution with doing idealized simulations. And finally, instead of reading these conclusions, I have to do publicity for the journal I'm about. And so this is a new journal. If you have research, consider to submit to our journal, which is now online and publishing and getting a good publicity, online attention and things like this. So with this, I would like to conclude.
Thank you, Brett. Questions or domande? Curiosities?
So if you think about how we simulate the teleconnections between El Niño and low frequency variability of Europe in the current model, say season system 4, season system 5, UK Met Office model, where, I mean, they're not perfect because in fact the forecasts over Europe are still quite challenging, but where do you think we need to improve more? What is missing? Any hints?
Okay. If my name was Shukla, I would say we need to resolve the tropical convection probably better to get a better idea of the actual source for these waves that eventually get to Europe. On the other hand, so that would mean you really, if you want to resolve convection, you probably need models of a resolution of, I don't know, 1 kilometer or something like this. On the other hand, I'm not 100% sure that one could be also be able to parameterize the convection better in a way to simulate these wavelengths better. So, but I guess the tropical convection could be a major source of uncertainty here, because that's the first and main forcing for the seasonal teleconnection. I mean, as you know, our ability to do seasonal predictions, I would say, is mainly based on El Niño, on the El Niño phenomenon, which is persistent and quite good predictability, and that the sources for those teleconnections are the upper level divergence, which are driven by the convection that is triggered by this event. So, but this is not really a response that is coming from my own personal opinion. I think we could still try to improve convection schemes to get that better.
But what do you think about the way we simulate the interaction between Rossby waves and the stratosphere? Are we good enough, or?
Oh, I think, for example, the UK Met Office researchers, they claim they have such a good representation of this phenomenon, of the interaction of, for example, El Niño with the stratosphere, that they can get North Atlantic oscillation predictions up to 1 year ahead even, because there's some skill in predicting tropical SSTs 1 year ahead, as you have shown. And so they get some skill in predicting the North Atlantic oscillations. I would say it's not so bad. But on the other hand, even if you can predict the North Atlantic oscillation, there's a very large scale index. There's no guarantee you can predict any local climate in Europe, because the signal in Europe may be very weak or something. So, yeah. But I don't think there's any, perhaps models show diversity, but in principle, I think there's, it seems to be at the moment a good hope that these, for example, tropospheric, stratospheric interactions work go in the right direction.
Other questions? Or you mentioned this last point of this open issue, this open question that you raised. Is there, I mean, there are ways, different ways to approach it, or
yeah,
I mean,
yeah,
assumptions that can be proved or not?
I think idealized experiments in this case are necessary, because you cannot use neither observations nor the forecasting systems that are coupled, have complicated interactions to do this, because this Rossby wave source is extremely noisy, and it's not always clear that, you know, sometimes the wave, the response itself causes what seems to be a source, but it's actually not the source. So you would need to do idealized simulations, for example, with the ECMWF model, to put a localized source, for example, in the Atlantic region, to see if that can effectively provide such a wave train to Europe.
So we need to understand.
Definitely, because it's important.
Yeah.
Yes, it's important, because it could be just by chance that we see in this period this signal, but we have to understand where it's coming from in order to be sure that it can be used as a predictor for European climate. Yeah.
Okay. Thank you, Fred. So we are ready for the last presentation, not the least, of course, from Alessio Bellucci of the Euro-Mediterranean Center for Climate Change in Bologna. And Alessio will probably bring us into the kind of climate prediction. So we will have temporal scales even longer. Please.
Yeah, it's actually taking longer even in uploading the presentation. Hopefully not decades, but decades or seconds.
You're a climate
PDF. It's a climate PDF.
Maybe the PDF.
Maybe PDF
we can probably close that.
Okay, thanks a lot, first of all, for inviting me, and also for shaping the workshop in such a nice way, so there is a very good hierarchy of presentations. And yes, so this is about decadal climate predictions. But before I get there, what I'm going to do here is to basically make an overview of this quite recent branch, and this is a kind of newcomer in the family of climate predictions. It's the latest arrival, so it's fairly new. And so before I get there, I'd like to make some step back before. This is a sort of provocative question, but this is the kind of question that we very often face, especially from people outside our, let's say, working environment. How can you predict climate for the coming decade if you cannot predict the weather next month? So this is kind of obvious for many of us, for all of us actually, but for many people this is not obvious. This is the sort of question that we need to address, whether we like it or not. And I'd like to thank Roberto for making a very nice, presentation before, so I don't need to spend much time on this kind of things, because this is all very known, old-fashioned style stuff. But this is, in order to understand it, to fully address I mean, why can we actually try to predict climate on a longer range? We need to really make a kind of a brief overview of different types of predictability. We can actually, we have limitations in predicting weather because of some theoretical limits in the predictability of the atmospheric state. And as Roberto was showing, this predictability is actually the scale is actually space dependent, scale dependent. So let's say this applies for smaller scale kind of features in the atmosphere, and it's showing a plot from Lorentz, 1963, showing how the atmosphere shows a very chaotic behavior, so that very small perturbation in the initial states of our system may evolve into very rapidly divergent trajectories, and that makes actually the weather at such scale, for the scales relevant for this problem, quite unpredictable. On the other side, a kind of prediction doesn't aim at that. We don't want actually to predict individual weather patterns, or rather the purpose of the climate prediction is to forecast the statistics of the climate system, averaged over time and space. And this is a kind of exercise that we do, for example, in whenever we look at the climate projections. But the type of predictability we refer to in the climate prediction and projections, and I will show you later what is the difference between climate prediction and projections, of course. But the climate projections in particular refer to the predictability, say, of the second kind. This is a nice cartoon by Tim Palmer showing as a very schematic picture what does it mean, this type of predictability. Suppose that you have a kind of experiment where you have this dispenser of little spheres that can, depending on random perturbation, that they have equal probabilities of ending up in the left on the right side, so to say. But if at some point we turn on a kind of Deus ex machina, like a big fan which produces a unidirectional flow or wind, let's say, then the little balls will actually experience a forcing. It is an external forcing that pushes your system to be visited in a certain area of your phase space. And so, not surprisingly, there will be more balls that will fall in the left side rather than in the right side. So, assuming that we can then this is the type of predictability that does not rely upon the knowledge of the initial state, but rather on our capability of predicting how the external boundary conditions, or and that's another way of naming this predictability, boundary value predictability, because if suppose that we have a kind of ability of predicting the behavior of this external forcing, we may in principle predict how many, how likely it is that for example, the balls will end up in a certain part of my system, like on the left side, on the right side, etc. So if you step back from this analogy and you go into the real system, well, in the climate system, then you can substitute the fan with the radiative forcings, or the external radiative forcings, for example, the one that is exerted by the existence of emissions of greenhouse gases or other gases that have the ability of altering the thermal balance of the planet. So suppose that, for example, these two pictures are taken from the last assessment report from the IPCC, and they show what is the climate which is expected by the end of the century, based on a number of different climate projections which have been done by different groups around the world. And so this is an estimate of how the climate might change. And let's say the reason why we may believe to this kind of picture is because we think we have a broad idea as to how predictable is the external driver or the boundary conditions. In this specific case, the reason why we believe in this picture is because we have a broad idea as to how might evolve in the future. For example, the concentrations of, let's say, greenhouse gases or other important actors in the climate system. But this is the type of exercise that is so referring to, in particular, to the climate projections. Even though we have no precise idea as to whether we will be, whether we should embrace a more optimistic view and think that in the future we will be able to implement some, some mitigation policy. And in that case, this kind of large spread of different scenarios refer to the radiative forcings are due to different possible and plausible or supposed to be plausible evolution of the socioeconomic storylines, so that the red curve refers to a very pessimistic view based on which we will rely upon fossil fuels heavily in the future, and the blue line is the one that refers to a more, let's say, optimistic view that assumes that probably we will be able to be more, in a way, able to implement more mitigation. But that's each of these storyline is supposed to be plausible in a way, and that gives you an idea also of how uncertain could be the estimate based on this storyline. And that, of course, reflects in a similar uncertainty in the temperature, in the surface temperature evolution. And this picture just shows, based on these two extreme scenarios, the RCP 8.5, which is the pessimistic one, and the RCP 2.6, which is the optimistic one, that we actually don't know where we are going to end up by the end of the century, but we know that we might be somewhere in that region. And this sort of predictability, in a way, comes from the broad idea that we might have a future socioeconomic pathway we might follow in the future. But this is one kind of predictability, and it's not the whole story. This is what we refer to the climate projections. There are other drivers, there are other actors that actually modulate climate variability in the decadal and multi-decadal range. I'm actually here making, the previous example was a purely anthropogenic kind of example, but there are other external drivers, where external means something which is, not internal climate variability, not due to the interaction between different components of the climate system. So these are still exogenous sources of climate variability, like due to volcanic eruptions, for example, or the activity of the solar cycle. These are all, potential drivers of, they're actually shaping the climate. In particular, the volcanic eruptions, we know they are able to introduce some sizable drops in the surface temperatures. And you can look at the gray bands, which refer to some of the major volcanic eruptions. Not all the volcanoes, by the way, affect climate, and these are particularly basically the volcanoes that are in the equatorial area that are more able to connect to the stratosphere and therefore to alter the whole global climate. And so you look at the Pinatubo or other volcanoes, they manage to introduce some changes in the very reduction in the temperature due to this massive emission of chemical compounds due to the oxide of sulfate in particular. And solar variability is another driver of climate variability. But I'm making this example and I'm labeling as unpredictable. Basically, at the moment, we are not able to predict a volcanic eruption in advance. And likewise, we know that the solar cycle has an 11-year cycle, but that is not a primary driver. We know actually solar variability undergoes some very low frequency changes that have happened in the past, and But unfortunately, likewise for the volcanic eruptions, we are not able to predict these very low frequency changes in the solar activities. And therefore, even though these are the type of, let's say, climate variability drivers that we cannot take advantage of to for making a, let's say, skillful prediction over the multi-year or decadal and longer range. But going now to internal climate variability, that's another kind of subject, and it's another story, because I mentioned so far anthropogenic and natural drivers of climate variability, but there's a third category here, which is actually the one that refers to the internal dynamics of the climate system. In particular, what is internal climate variability is whichever comes from the complex interactions between ocean, atmosphere, cryosphere, land, all these systems without the intervention of any external, actor. Its own internal variability might be, in principle, predictable. But this is a nice picture taken from a paper by Mojib Latif and co-workers in 2006. And this is basically the linear sea surface temperature trend obtained by after removing the global mean trend. Supposing that this is the kind of residual trends that you get once you get rid of the, let's say, supposed to be anthropogenic component. So this is all natural variability, natural in the sense of internal, not external induced, but natural as internal variability of the climate. And you see that if you do this exercise, you end up with several spots which point you to the extratropics, in particular the North Atlantic and the Pacific extratropical FST anomaly pattern. And that shows you that there is, some very pronounced, component, variability component associated to the extratropics, to mid-latitude, and in the ocean. And I'll go back to this point later on. But if we zoom into, in particular, the kind of variability that are behind these signatures, and look at the time history of the North Atlantic sea surface temperature, or the extratropical sea surface temperature in the Pacific, you see that the type of evolution that you find shows some, quite pronounced multi-decadal-like variability. I mean, some people was bold enough to name this Atlantic multi-decadal oscillation, even though many authors dislike this terminology of oscillation, because it implies that we have an idea of that there is a real oscillatory behavior. Actually, others prefer to use variability, and likewise for the Pacific, PDO is Pacific Decadal Oscillation, or some other people prefer to name it as Pacific Decadal Variability. But whether or not it's oscillatory, you can tell that there is a quite low frequency residual variability in the extratropical oceans. And the question is, where does this come from? But that's a huge issue. Why is that? Suppose that we were able to predict in advance any of these low frequency modes or low frequency signal of variability. For example, this is again showing that the Atlantic multi-decadal variability is highly correlated with, for example, precipitation over Sahel, or to the intensity of the hurricanes, and clearly this point to extreme relevance of this type of signals, that showing that, for example, knowing in advance a fluctuation of the Atlantic multi-decadal variability would imply, if this correlation is robust, as it seems to be, it would imply that we are able to predict major fluctuations in the precipitation over Sahelian Africa, or over activity in the hurricanes. And as you can tell yourself, these are very important issues, and because of their impact on the people living on the continents, not only for the oceans, where basically nobody is living in the, we are not fishes, but the people living in these continental areas might be very interested in knowing in advance this kind of fluctuations. But the ocean is not the only part of the climate system that shows some low frequency variability. And keeping in mind that, I mean, variability might or might not be, I mean, synonymic of predictability, but it's interesting to notice that, for example, the stratosphere, as most of you know, of course, is hosting a very low frequency quasi-biennial oscillatory behavior, and then and this plots are taken from Baldwin et al. And Reichler in the lower panels, showing these changes in the zonal winds in the equatorial stratosphere, and also sudden stratospheric warming seems to be subject to low frequency fluctuations, in particular in terms of frequency of occurrence of this type of events. And there are alternate epochs during which these events might be more or less frequent. So, so the question here is, can we predict internal variability occurring over multi-decadal timescale? So this is the kind of question that we want to tackle, and this is exactly what the decadal prediction aim at, in a way. So decadal predictions lie in a kind of confluence between the first kind of predictability that I was mentioning at the very beginning of this talk, and the second kind of predictability, which is the boundary value predictability. So we have a kind of a hybrid problem, which somehow fishes from both sides. From decadal predictions rely upon our ability not only of taking advantage of the fact that we know that, for example, anthropogenic drivers will determine a given change in the temperatures or in other fields, but we also, in principle, if we may be able to initialize properly certain components of the climate system, and here I'm referring mostly to the ocean, particularly to the ocean, because the ocean is the, as we was looking at before in the previous slide, the ocean is this perhaps the slowest, slowly evolving component, the slowest evolving component of the climate system. So the decadal predictions are in between, and therefore they can benefit from both initializing correctly the system or rely upon the best estimate we can rely upon of the oceanic state initial conditions, for example, but they, of course, they are also benefiting from the second kind of predictability, and therefore from the boundary value predictions, and they are a kind of mixture of projections and prediction in a way. As I said, basically for the decadal prediction, the ocean has a primary role, plays a primary role. And I'm just showing this cartoon to introduce the problem with the ocean. So the ocean is a relevant component of the decadal climate prediction system, but we need to bear in mind that sampling the oceanic state is a challenge, because we tend to have a very patchy vision of the oceanic state. It's very, it's quite challenged to go on the ocean, especially in certain areas, and measure in real time. We can have a good view of the ocean surface, but there's a big issue of the subsurface ocean, which is much more poorly known and measured, and therefore, and of course, whenever we talk about the decadal scale, the subsurface ocean may come into play, and therefore we cannot neglect what happens below the upper 100 meters. But things are changing, fortunately. This picture is providing history, a short history of the ocean measurements. The ocean has been very poorly observed before the early 2000s. So you see that there is the color. Whenever you see the color, it means that is the belt of the ocean that we were able to sample up to now, and there is a very little, well, that's depth in the y-axis and time on the x-axis. So back in the 80s up to the start of this millennium, well, our knowledge of the ocean was like mainly appropriate for the upper, like 700 meters, let's say. But there is some kind of a Copernican revolution happening at the early of the 2000 years, but you see there is a sharp increment in the depth of the sampled ocean going down to 2000. And then what happened after the year 2000 or 2001 and 2 is that there was a very important observational program that started with the deployment of Argo floats. And these Argo floats were not only provided, well, they were drifters and providing their location to by remote, and therefore they were not only allowing to measure the currents through their drifting motion, but these drifters were also able to go underneath the surface and take samples of the temperature and salinity, go back to the surface, transmit the data, and that provided a much finer, knowledge of the ocean in terms of their depth structure down to 2,000 kilometers. And then this program needs to be, of course, needs to go ahead because we need this data in order to better constrain the oceanic state. But as I say, things are getting better and better because the Argo program is giving us a new vision of the ocean state. So what is the decadal prediction system in a nutshell? But this is not much different from any other operational system. I must say that decadal predictions at the moment are not operationally operated. There is not at the moment no decadal prediction operational system, although there are projects and plans to let this happen. And so far, decadal predictions is more like kind of a scientific exercise that quite different groups are undertaking. And but in a nutshell, the decadal prediction system relies on a dynamical model, a set of observations, and of course, we need a data simulation system in order to nudge or constrain a dynamical model with the ops, and so get with a accurate as possible estimate of the state of the climate system, in particular of the ocean. But in principle, there are other components that might provide skill on a multi-year range. But let's stick to the ocean. At the moment, that's the main component that is on which we are relying. So as I say, this is a really new exercise. The oldest perhaps exercise in terms of decadal prediction date back to the 2007. There is 2008 and 2009. These are three seminal works by Doug Smith from Met Office, Noel Kimiside, and Holger Pohlmann, and this is like represented all together here. And these were the very early attempts towards reliable decadal predictions. And these studies were quite pioneering and paved the way to have this type of prediction, decadal predictions, enter into the IPCC exercise. In the latest IPCC Working Group 1 fifth assessment report, there's a specific chapter, it's chapter 11, where the near-term decadal prediction, there's a protocol, of course, and several groups took part of this exercise and produced different, they produced the decadal prediction for the period which goes from 1960 to 2005, actually. And so this is a picture taken from the AR5. I just want to, what is the skill? And that's a sort of obvious question. Are we really able to predict climate fluctuations on the decadal time range? These are the kind of metrics we look at. I've actually taken exactly from the seasonal forecasting toolbox or even well forecast, to be honest. This is an anomaly correlation, is a measure which gives you the idea of the how well correlated are the simulated climate and compared to observations. This is based on 6 different European climate prediction systems, and it's based on the multimodal ensemble mean over 2 different time range, 2 to 5 and 6 to 9, which is kind of standard. And whenever you see red or yellow, it means that there is a very high skill. Whenever you see, bluish, it means, or even pale red, it means that the skill is poor or almost 0, or is negative, which in this particular case means that there's no skill. And well, you might be surprised looking at this picture because you see lots of red or yellow. You say, well, what's going on? Are we really able to predict all this stuff? Well, the thing is that, as I was saying before, the clinical climate predictions are a mix of climate projections and real predictions. So lots of this skill does actually come from the global warming signal. So we are actually predicting that the world is going towards a warmer climate, but that's not a particularly exciting news because we can tell this already from projections, from standard projection. So in order to evaluate the added value of the decadal prediction with respect to more standard climate projections, we need to remove or detrend the signal and look for the residual predictive skill. One we remove and we take off the component which is due to the boundary value predictability, and we only are left with the initial value predictability component or predictive skill, and that's the real picture that we get. So we see that now there's a much less predictive skill once we remove the global warming signal. There's a lot of blue all over, particularly over the Pacific, but there is still some sizable fraction of high skill, in particular over the North Atlantic, where I'm putting some like a black frame, and there is some interesting predictive skill also over continents, over Southern Asia or parts of the Africa continent, and this is based on 6 different models, but particularly the North Atlantic skill seems to be one of the most robust features of the decadal prediction. It looks like we are really having some skill over that area. If you look at the precipitation, well, the picture is much more noisy. There is some skill, actually, particularly if we look at the longer lead years. The lower panel refers to 6 to 9 lead years. And you see that there is this redness over Saharan, over Africa, and parts also over parts of Europe or Eurasian North America, which is kind of promising. But outside of those regions, there's a lot of noise and skill. I mean, it's questionable whether we really have some real predictability over there or predictive skill over there. But there's another way of looking at skill in decadal prediction, and I like to emphasize 2 specific events. So we single out in the recent past 2 specific events and see whether, the decadal forecast system managed to capture these 2 specific events. These are the mid-90s Atlantic warming. In the middle of the 90s, the subpolar Atlantic basin underwent a major warming. The other one I'm going to refer to is the hiatus that has been lots of discussion about, which occurred at the turn of the millennium. And first, I'm going to show you something from the mid-90s warming. So as I was saying before, the upper subpolar basin in the Atlantic underwent some kind of major shift. If you look at the 1986-1995 average anomaly over the subpolar basin, is mainly blue, and if you look at the picture on the right, is the 1996-2005 average anomaly is red. So there's set of major changes, that's a kind of step change in the temperatures of the subpolar basin. So some researchers, Ring Sadek, made this very nice assessment using the GFDL predictions, and you see that the red curve refers to the predictions, is the initialized, meaning that there was an initialization of the oceanic state, whereas the blue curve is the non-initialized, which is more like standard projection without any, with just an arbitrary initialization of the climate state. And you see that while the red curve managed to follow the jump in the temperature, which is the thick black line, the blue one is actually failing, is like producing a drop in the temperatures in the subpolar basin. So meaning that there is actually looks like initializing the ocean provides some added value, and it looks like this specific system was able to reproduce, but it was not the only system which was able to reproduce this event. The global warming hiatus is another issue which has received lots of attention. And what is it? This is a change in the trends. Basically, in the last 10, 15 years, there will be, if you compare the global mean surface temperature for different seasons, you see that the latest part of the record is a kind of plateau. So there's a change in the trend in the global mean temperature, which doesn't mean that, I mean, well, we know that some of the warmest years in the climatic records in the last years. The major change was only in the trend, in the slope of this curve. And so there have been studies that actually show that this hiatus seems to be traced back to a cooling in the Pacific region, in particular a change in the phase of the Pacific decadal oscillation, which determined this regional cooling over the equatorial Pacific and also in the extratropical Pacific. But apart from this area, I mean, the rest of the world were actually keeping on warming. But the question was, were we able are we able to retrospectively predict this hiatus, this slowdown in the trend? And the answer is actually yes. This is another good example. Virginie Guémat and other colleagues published this article showing again the comparison between the standard projection where no initialization is applied to a model and a prediction. This is based on one model, I believe. It's the Easy Earth model, and the prediction is the decadal prediction where you actually constrain the oceanic state. You can tell that the projections are actually failing in reproducing this plateau in the global mean temperature, whereas the initialized prediction are more able to capture the hiatus. So I'm basically finishing here. I'm just showing this picture from the cover from BAMS in May 2012. At the time, it was really, I mean, one of the earliest years in the decadal prediction. The title of this of the article by Lisa Goddard, to which this picture refers, is a seasonal and decadal prediction helping each other grow up. And of course, the grown-up child on the right is the seasonal forecast, whereas the decadal prediction are the little child on the left. But they are holding each other's hands, meaning that they can help each other. Well, in fact, I think there's a lot to learn from each other exercises, and for sure, decadal prediction. I mean, they benefit enormously from seasonal prediction experience that has a much longer history, but the decadal prediction are little, but they are growing. Through the years, we will see this will become an adult, we hope. And so I'll finish here.
Thank you, Alessio. Domande? Please, Fred.
One comment, one question. Of course, now the hiatus, if we draw the global temperature after the latest El Niño event,
Yeah.
again.
Yeah.
Okay. The question was, it seemed to be quite amazing, this popping up of the 6 to 9 year prediction skill in the Pacific, in the subtropical Pacific. It's something new. This one.
Yeah.
It's quite amazing, isn't it?
This is kind of interesting, but I don't have an answer to this. What does it come from? This is 6 to 9 years. Is a strange beast because you are quite far away from initialization, and most of the people usually look at the 2 to 5, and the 6 to 9, in my opinion, is still might be, contaminated by boundary value kind of predictability rather than purely initial value predictability. Because
and also the signal that you see in the Middle East, do you think this is coming from Atlantic, or is there any other hypothesis for this?
That's a good question. It's another mysterious feature, but I guess it might not even be the same macro-region. It's like now I'm framing it as a one box, but it might be it's collecting contributions from different sources. I'm not quite sure what happens in the Far East. Can be, as well, has the same source as the Mediterranean. The Mediterranean skill is actually AMV driven mostly. So I would rather say that this picture is misleading because it's the AMV on the Atlantic which is driving a lot of predictability on the Med Sea. If you look at the SST in the Med Sea is actually going hand in hand with the AMV. So the AMV is a very good predictor of SST in the Atlantic basin. So I would say that we should rather split that box in two pieces. And but I have no idea as to what happens in the Asian part of the skill, and we should challenge this picture with the CMIP 6 and see whether it is robust. Yeah, but this is still based on 6 European models. It's not just one model.
Yeah.
I think that the prediction that you have presented are based on dynamical models. I'd like to know what do you think about the data-driven methods in order to get decadal forecasts in climatic science.
So you need statistical forecast,
yes,
or
yes.
Instead of the key
statistical forecasts based on statistical models?
Well, yeah, sure. I think, but this is sort of very pioneering thing, and I know there are people who are, willing to exploit this specific approach to the decadal prediction as well. But yeah, I don't. Well, what I think this is something that we should try to explore. Whether it is useful or not, I'm not sure. But in the seasonal forecast application, statistical approaches are used, as far as I know. Yes, running a dynamical model is very demanding. So one way to overcome this heaviness of this exercise is the one that you say. But I don't know much about the skill. Maybe, I don't know if Fred knows more on that, on the statistical forecast, but in the seasonal case.
For ENSO prediction, there are statistical models. Some people claim statistical models are probably, in some cases, beating the dynamical models. But then in a dynamical world, if you use a model, everything is consistent. Mm-hmm. So you have one kind of instrument that should be able to link everything consistently together. Whereas statistical models, you may have decadal changes that destroy things. And, I don't know.
But yeah, on this point, about, if I remember correctly, at the end of 2008, 2010, there were a couple of papers that showed that for seasonal prediction, dynamical based predictions were better than statistically based predictions. And then so we started doing seasonal prediction maybe at the end of the 1990s, 2000, and for the decades they were both statistically based and dynamically based and had similar skill. But eventually there were a couple of people that really showed that dynamical methods were better. So in fact the question was for decadal prediction, do we have already evidence that with dynamical model we can do better than with statistical methods? Or I don't know, I'm not aware of.
No. Well, there are, well, for example, there's a paper about tropical cyclones. If you think about trying to predict the count of the tropical cyclones, if you want to do this exercise with the dynamical model, is a huge effort. Though people from Met Office has done it, but that's the kind of example I can think of where a statistical predictor may work better rather than, I mean, a dynamical model. In terms, if you believe that the SST is a good predictor for tropical cyclones in the Atlantic, I'm just guessing, or some other predictor, then why not using that one instead of using the whole machinery, which is huge? But the tropical cyclones are a specific beast, and I don't. Maybe that is the kind of example I can think of with some success. There's a work by Gabriele Villarini, Gabe Vecchi, people at GFDL, looking at this with this kind of approach, and some people in Europe as well.
Yeah, Paolo, please.
Is there a roadmap to operational different predictions?
Yes, there is actually. I didn't. Well, I should have updated my my presentation to include this point. For brevity, I wouldn't. But the WMO is already, well. Near-term predictions have become a grand challenge recently, and one of the grand challenges which are endorsed by the WMO basically, and then that was an important step. So, but this is paving the way to have, at least in Europe, I think, I don't know in other parts of the world, in Europe there is a real will to have an operational decadal prediction system. There's a project which is called EUCP, which is an H2020 project where we are involved, and it aims at, you know, building the way towards going to European kind of prediction system. There's already an ongoing effort of collecting decadal kind of prediction from several groups, well, not only in Europe but also elsewhere. And the Met Office is providing yearly a decadal forecast from now to 10 years, and it's repeated every year. So this is also a kind of pre-operational sort of exercise, and the forecasts are available in the multi-model and multi-model ensemble mean for several variables, and so there's a lot of going on. And yes, I think WMO is actually willing to, I mean, to facilitate this kind of path.
Just to mention, what about the ensemble decadal prediction? Is it actually the way to go? I mean, what's the link? I mean, is it the same approach?
Yeah.
Theoretically speaking, or is there a difference?
I skipped some technicalities but essentially the way we perform decadal predictions is the same as any other kind of prediction. We run ensembles, and which are initialized every year now from 1960 to present, basically, and for each year we provide hindcasts which are 5 to 10 years long, and there is a minimum ensemble of 10 members, because we cannot have, well, there is a huge effort running 10 years hindcasts for, you know, tens of members. So, but the mandatory is 10 members ensemble. In C5 is actually, it was less than that. It was 3, but it was clearly, I mean, 3 is a ridiculous number of this, extracting this kind of signal. And yes, but basically the approach is the same, except that we cannot afford the same size of the ensembles as for numerical weather prediction or seasonal forecast.
So this means that actually the trends are actually illustrated as probabilities of variable over the globe. So we are talking about probabilities exceeded in terms like it is in PDF.
Yeah, we can build up the same sort of there's a problem as to how do you merge the projections and the predictions. There is this problem of seaming together these two pieces of information, because again, I didn't go too much into the details, but whenever you initialize your dynamical model, your model will tend to drop down or to go down to its own attractor, because models have biases. So you have a lot of these spurious signals. You need to get rid of these signals, otherwise this drift will contaminate, whereas the projections don't suffer of the same problem because they are not initialized. So the models are always relying nearby their own mean state. And therefore, in order to combine together these pieces of information, build up, for example, PDF, but putting together the decadal and the multi-decadal projection information, there's a lot of, you need to do something. And there's something that, for example, we will tackle this issue, for example, in this project, in this UCP, but it is a challenge. Yes. But the toolbox, that we use is actually taken from the past experience in forecast. And weather and seasonal forecast provided a very excellent basis for us to start this kind of exercise. The kind of toolbox is similar, even though the processes are different.
Yeah, please, Lorenzo.
We talked before about statistical models, and specifically about bias correction. Is it plausible, in your opinion, to apply to climate prediction, that is different time scale than climate projection, the same statistical techniques as quantile mapping and thinking of in a seasonal or even better decadal prediction? Does it make sense in your view?
Possibly, but I'm not sure. I'm not. I don't know, because we have, as I was saying before, we need to deal with the bias.
Yeah.
And therefore, but the way we deal with it is not at the moment is not based on the approach that you say. Yeah, but there are people who try this kind of approach applied to decadal prediction. It's a very pioneering field, but currently what we do is we need the biasing is actually more the drifting, because the model is drifting. It's not just it's not only bias, it's a time-dependent bias. Yeah. So we need to know this, that the primary source of error in our case is this drift. So that's our primary objective. It's not just the bias that you shift your model up and down.
The problem is the different time scale that we are considering on climate projections and the climate predictions. So in the climate prediction, you need to correlate with time, while with climate projections, we are in some ways released from the time correlation. So we think only to the PDF or the statistical distribution. So this is maybe a weak point. This means apply to prediction. Maybe.
Okay. Do you want to predict the evening? From now, I don't know if there are other issues, comments, and I will really thank all our colleagues, Roberto, Fred, and Alessio, for having accepted our invitation, and it's really a unique opportunity. Unfortunately, we had to choose a day. So, but actually, this homemade streaming is still opening these seminars to a broad audience. So I would really have to thank all the people, and especially Ida, who is actually connected to set up, and all the group that actually working on this communication aspect as well. And also I have to thank Paolo, because if we were able to put all these seminars all together with a thread which will naturally evolve through the presentations, it's actually thanks to Paolo and to the availability of our friends, and also I think Paolo also defended his PhD thesis cum laude this morning, so I think we can make an applause to Paolo as well. Okay? And I think also the success of the PhD work of Paolo is also thanks to you all.
Well, and thank you to you and Chetan for organizing and funding this, because I think it's great that we had the chance also to hear such a nice, I think, set of talks, one following the other.
Yeah.
We touch a lot of very important topics which are very actual and very hot.
Yeah, actually, you know what we noticed that also the local media were actually sensible to this. We were just letting the news. We have a workshop. Local newspaper were actually noting it and sending. So the science may have also an appeal. Ok, so grazie a tutti, buonasera e buona serata. Buon lavoro.
Okay.